All right, in this lesson, we're going to expand our idea of percentage growth, exponential growth, to tackle a variety of contexts using interest. So what we mean by simple interest is that my future value, f, is given by my principal times 1 plus r to the t, where r is the rate, p is principal, and that's just your starting value, and t is time. So this is the same thing we've been working with. P is just a number, another name for B. Principal is kind of the finance term for this. So we're going to start to consider some special versions of this that occur often in real life when you're dealing with like personal finance, and we're going to use them to develop our understanding of like how we can transform exponential functions to represent a bunch of contexts. So as we start to consider these questions now, the second question is an easier question. So it says we have a 100% interest rate, which is a very magical bank indeed, and we're putting $1,000 in there. Well, our future value would be R is 1, right? T is 1. Well, this would be $2,000, right? So it doubles your money is 100% interest. That's what that means. And then the first question is just kind of a real life kind of thinking question. So would we rather be paid now or later? You're probably thinking now, but you're probably not thinking now for the reason that like rich people think of now. Rich people are like now because then I could earn interest on it. We're thinking, we're normal people, we're like now so I can buy stuff, right? The kind of finance interpretation of this is it's always better to have money now because you can earn interest on that money, right, by putting it in a bank for free. Okay, now we're going to make this a little bit more realistic. We're still going to use our $1,000 because the values are easy and the 100%, but we're going to consider quarterly interest, right? So quarterly interest would be we take our 100% and we divide it by 4 quarters, which would equal 25% each quarter. And then, well, we would have $1,250 after 1 quarter. We would have $1,562.50 after 2 quarters. We'd have $1,953.13 after 3 quarters, and then over $2,000 at the end of the year. $2,441.41. And hopefully you're wondering how I'm getting these numbers. The relationship is exactly what we've studied before. We're doing times 1.25 each time. And notice every time we do this, we're using repeated multiplication. So I could have represented this as 1.25 to the 4th power, right? So as we fill out this table, make a prediction, like what's going to be worth the most money? Like what is the best situation for you? Monthly, of course, means 12 payouts per year. Weekly is 52 payouts per year. Daily is, of course, 365 payouts per year. And then if we're earning 100% interest, we're dividing that each time by the number of periods, right? Because otherwise it wouldn't be a correct comparison. And this is the convention, how we represent these things in real life as well. So the way I would probably calculate these is using our simple interest formula, right? So here I would do 1,000 times 1 plus the rate to the 12 months would be my exponent. Here, same thing, 1,000, 1 plus the rate to 52 weeks. And then here, be careful with your decimal points here, because it's quite a small daily interest rate. And here are my future values at all of these different interest situations. And as I start to evaluate these, we will see that the more often interest is added, the better off you are. And that makes a whole lot of intuitive sense, I think, right? Okay, so now let's develop sort of a general formula. So we kind of just use logic to write each of these. Our general formula is going to involve a transformation. So we're going to be like f of t again, is the principal times 1 plus r over n. And then my exponent is going to be n to the t. Or sorry, n times t. And then we already know r is my rate, but it's annualized. So it's how much is my interest rate for a year. So it makes sense that we're changing it in our formula. We're dividing it by n. N is the number of compounding periods, and p, again, is the principal, and t is time. Okay? This, by the way, is an n up here. Make sure it looks clear. So all this is a transformation of our original function. And notice what we're doing here is our n is a horizontal transformation. Specifically, it's a compression, right? So it makes our function grow faster. And if I divided by n, I'd be making it grow slower, right? And then the n in here is just because we want that rate to represent a yearly rate just by convention. That's how it works in real life. Okay, so a couple of quick examples. I'm not going to solve these, but I'm going to give you the setup. So quarterly means n equals 4. Daily, of course, means n equals 365. And then my setup, right, would be 100 equals 1 plus 0.03 over my 4. And then up here, 4 times 50. Okay, so notice it makes a lot of sense that my exponent is, 200 if we're going 50 years, because it should be a lot bigger if we're compounding 4 times per year, right? Same thing here, 1 plus 0.03 compounded daily. And again, my exponent would be way bigger than 50 years, right? So we would expect this to be the best deal here. All right, the last thing I'll give you is a couple other interesting ways we can use this. So we have initial value of 400, right? Growing at a rate such that it doubles every 8 days. Doubles every 8 days. And we want the quantity after 29 days. So here, we can be like, f of x equals 400 times, if it doubles, well, my base is going to be 2, and then to the x over 8. Because remember we said dividing by that number will make our exponent grow more slowly. So if a plain old x is doubling every 1 day, x over 8 is doubling every 8 days, right? And then if I want f of 29, doing 400 times 2 to the 29 over 8. And I'll let you solve that one on your own. That's just a calculator problem. Last thing, we have a bacteria starting off at 850 and growing exponentially at 8% per day. So it'd be like 850 times 1.08 to the t. And we want to change it to an hourly rate of change, right? So an hourly rate of change, well, there's 24 hours in a day, right? So this was our daily function. Hourly is going to be 24t is going to be my exponent, so it should be growing faster. And here is the trick, right? If I raise that outside power to 24 as a shortcut, I can raise the inside to 1 over 24. Because for that particular piece, this particular base, that will cancel out while still causing our exponent to grow a little bit more quickly. And then when I type that into my calculator, I get 850 times 1.0032 to the 24t. Okay, so that's my new function. So notice the way we transform these things is by changing the exponent to grow faster or slower.